do a couple of more. Yeah, so we'll do a couple of more examples of the application of vertical motion, and we'll start the next section of kinematics after that. Okay, so one important thing we saw yesterday is when we have a vertically projected motion, there is a symmetry in it. So if we project something vertically from the ground and it comes back to the ground, so what we saw is that if it has an ascent along this line, when it reaches this point where velocity becomes 0, that is exactly half the total time of flight. Then after that it descends. And comes back and hits the ground with the same speed but the opposite velocity. So the impact velocity is again u in magnitude. And the total time is 2u by g. But on the way up, if it had a velocity v1 at some time t1, then on the way down it will be at the same position, having the opposite velocity of minus v1 at time t2. Now that t2 will be t minus t1. So this was the symmetry of that vertical motion. Ascent versus descent. And then of course we saw that maximum height is given by u square by 2g. The easy way to remember this is that potential energy comes from the initial kinetic energy. Even though we are studying kinematics here and not work energy, but this is a very easy way of remembering this formula. Anyhow, so now we will look at a slight variation of this. So we will look at vertical projection. So you can think of this like a next case. Okay. From a height. So we will actually do this case with a direct example. So what is happening in this example is, suppose this is our ground level. And this is some heighted position. Now a person throws up an object at t equal to 0 with some speed u. And this height here is 300 meters. And this object goes up like this and then comes down. He doesn't catch it on the way down. So it impacts the ground at some time t with some impact speed vi. Okay, and we'll take g as 10 meters per second square. So suppose t is equal to 10 seconds. Then we have to find u and the total distance traveled from 0 to 10 seconds, and the time of ascent, it is how much time it is going up for, and descent, how much time it is coming down for before impacting the ground. Okay, so this question will also clear for you, the whole concept of sign convention and how to use quadratic equation and all these things. Okay, so just start with this question, people will discuss, work it out and send me the answers. No, Arnav, I think what you have done is you've applied the formula directly. But see here, it is not coming back to ground now. So total time of flight is not 2u/g. It's going past ground. If you remember the derivation of the total time of flight, it was done by taking the displacement equal to 0. But here, when it reaches the ground, is the net displacement going to be 0? No, no. It's 300 meters below the starting point.
Yes, sir, understood.
Understood, no? So you have to make that adjustment over here. Yes, Sanya, very good. That's correct. All the parts are correct for the answer.
Sir, are my answers correct now?
I'll just check, beta. Just give me a second. Okay, yes, very good. All your answers are correct. Arnav, Arlene, Aparna. Okay, so we will get u as 20 meters per second, as all of you got. Okay, we will get the total time. Achha, that's already given. So this total time of 10 seconds is actually 2 seconds for ascent plus 8 seconds for descent. So very simple thing you have to do here is you take your origin at this point and you take this as your axis. So I'll, for example, take this as my y-axis. So we'll say that at t equal to 0, my initial y coordinate is 0. My initial velocity is plus c, which I don't know. But my acceleration from that point onwards is minus 10 meters per second square. So at any time t, my y is equal to y. So the displacement is equal to y. So that displacement is equal to, because displacement is final minus initial position. So I've taken the origin here. So my displacement should be equal to ut minus 5t square as usual. Okay. Now you can see that at t equal to capital T, which is given 10 seconds, my y coordinate is how much? It is minus 300 meters. So my displacement is how much? It is again minus 300. So that's one way of doing the question. Okay. So put this information here now. Okay. This information that at this time that the displacement is this much. Put this information in this. So this equation becomes this. That minus 300 is equal to u into 10 minus 5 into 10 square. So that's not even a quadratic equation. This will just give u as plus 20. Okay. And once you got this, now you can see that at t equal to t1, suppose the velocity becomes 0. That means it's reached the highest point. So the highest point is 0 is equal to 20 minus 10 t1. Because also you will have the second equation of motion. So this t1 will become 2 seconds. Okay. And therefore time of descent, that becomes t minus t1 or 8 seconds. So that's done. Okay. Now also you can see that displacement from t equal to 0 to t equal to t1 or 2 seconds, that is distance in ascent. So several ways of doing this. You can write this as directly by formula, or you can see like this, that it started from here at 20 meters per second, and 2 seconds later its velocity was 0. Okay. So during this interval of time from here to here, what is the average velocity? It's 10 meters per second. So the displacement is average velocity into time. That's another way of doing this. So it's 10 into 2 or 20 meters. Okay. This is another way of understanding this part. Okay, so anyhow, so this is 20 meters, and therefore distance in descent, okay, is equal to 20 plus 300, because it's gone up by 20 meters and then coming down 300. So distance we will write without sign. So that's 320 meters. So total distance from 0 to 10 seconds. This is from 2 to 10 seconds. That's becoming 340 meters. That's the final part. Okay. So this is one way of dealing with the question in a very formula based kind of method, and in a standard kind of method that we have discussed, that you always take the origin at the starting point and the initial direction of motion as your positive axis and all that. Okay. So I'm sort of following a standard format, or we can say a standard kind of method of solving the question. I'll show you some variations of that also. Okay. So here, importantly, what I have taken, so let me refer to the diagram also here. So in these equations, I have taken the y-axis as upwards, okay, and origin O at starting point. Now, there are some variations I can use of this also, which I'll discuss. Okay, but it's very important to understand what I've taken as the reference frame, so that you understand how I've substituted the displacement as minus 300 at the time of 10 seconds. Sign convention thing is very important. Okay. Okay, so any doubt or question? Yeah, I'm scrolling down, Bhavika. Okay, so this is clear to all of you. Now, another way we can solve the same problem. In fact, another couple of ways we can solve the same problem is that minor variations in how we choose our reference frame and all. So another thing we can do is take we can take our origin here and take our y-axis like this. So then what we will say that at t equal to 0, the initial velocity is some plus u which we don't know, but our initial position is plus 300. Okay, and our acceleration is minus g or minus 10 meters per second square. So when it goes up and then comes back and hits the ground at capital T equal to 10 seconds, our y will have become 0. So our displacement, which is y minus y naught, would still be minus 300. So, when we write the equation like this, that instantaneous velocity, which is dy by dt, is u minus gt, we have delta y is equal to ut minus half gt square, and that delta y is displacement. So this is at the derivational level. This is how this equation comes. So this delta y or this displacement is basically y minus y naught. So that is equal to ut minus 5t square. So at t equal to capital T, this will become 0 minus 300. Like this. So this is just a minor variation of where we are taking the origin, not a very drastic change. Okay. Now, one very drastic variation of this would be if we take the y-axis downwards instead. I'll show you that also. So it's not that you always have to follow some hard and fast rules for taking your reference frame. Okay. But generally, if you're confused about how to take the reference frame, then you can follow a general guideline that take the starting point as the origin and the direction in which it sets off. Immediately at t equal to 0 onwards, whatever direction it's going in, take that direction as your positive axis in 1D motion. You can use that like a guideline, but you don't have to strictly follow that. Okay, now the next variation of this we will do, as I told you, is one where we'll take the y-axis as downwards instead. Okay. That's also an interesting way of writing the equation. So when you project it with some u at t equal to 0 like this, one interesting thing we can do is we can take the y-axis downwards and take this point as our origin. Okay. So this distance being 300 meters. So what we'll see is that when it reaches the ground at t equal to capital T equal to 10 seconds. So if you take y-axis downwards, then our initial velocity is some minus u. Okay. or we can leave it u also, but it will come with a minus sign. Okay, and our acceleration is going to be plus g, or plus 10 meters per second square. So our displacement as a function of time will become minus ut plus half gt square. Okay. Or here y naught is 0. So displacement is equal to t equal to t. Y is equal to y. So displacement is equal to y minus 0. So that is this. Okay. Now in this we'll substitute that at t equal to 10 seconds, the displacement is plus 300 meters. So plus 300 is equal to minus u into time plus 5 into 10 square. So this is the equation we'll get, and as you can see, this will also give the same. Okay. So in this case, upward displacement is written with a negative sign, and downward displacement is written with a positive sign. So you can also play around with the sign convention like this. Okay, just as I said, in a question you have to be consistent. In between the equation solving from one part of the motion to another, don't switch this thing, Don't switch the sign convention in between.
Sir, what was the total displacement in this sum?
Total displacement is 300 meters, beta, but total distance traveled is 340. Okay.
So displacement will be minus 300, no?
Yeah. So see that is like according to our sign convention. In the original solution that I gave here, I'm taking the upward direction as positive. So the net displacement is minus 300. Okay. But I can also take the axis downwards like I've done in the third case. In that case, I'll write the total displacement as plus 300 meters. But important thing is the displacement is 300 meters in magnitude and its direction is downwards, vertically downwards.
Yes, sir.
Understood? No? Okay. So, and whereas the total distance traveled is 340 meters. Okay, and distance is not with any direction. So,
Yes, sir.
okay. So that becomes a fact. Now, another, before we move on, just one last thing, another slightly abstract way of solving this question would be that we could go without the equations and we could just look at a velocity versus time graph. Again, taking upward direction as positive. Our axis is upwards. So if we look at a velocity versus time graph, it would be something like this here. Okay. Where this u is unknown, but the slope of this is minus 10. And at this time, which is 10 seconds, the total area, that is the displacement from 0 to 10 seconds, with this axis in mind, that should be minus 300. So that way what we can do is we can take this time as some t1. So we can see that this area is plus of half of u into t1, and this area will become how much? This is some minus v impact speed, let's say. Okay, so v impact into t minus t1. Okay. So this is equal to 300. Now you can see that since the slope is minus 10, okay, so t1 is basically equal to how much? It is u by 10. So and again, since the slope is minus 10, this v1 is minus 10 into this remaining time. This remaining time is t minus t1. And then t1 is again u by 10. Okay, so this becomes u square by 20 minus of 10 into, now this is 10 minus u by 10 whole square. This is equal to 300. So you have u square by 20 minus, when you open this bracket, you'll still have a u square by 20 term, and you'll have another 1000 term, right? And you'll have minus 2u, this kind of thing. So from this also you can solve for it. So this is a bit of an abstract method. Okay. Not extremely convenient here, but oh sorry, this is oh, there's a factor of half. My mistake. Okay. So there is a factor of half here. So this actually, this u square term will not cancel out. Okay, so it will become a quadratic equation in u. So it's a little bit tricky. So this is not, at an absolute level a very nice method. Okay, but all right. So we're almost done with vertical motion. Just one last thing. Yesterday I was telling you about a question where there was negative root of time and how to interpret that. So let's understand that. So that also we can understand from an example like this, that suppose we project something. Now this time the projection speed is given to us. U is, let's say, 10 meters per second. And then what happens is this height is, let's say, 160 meters. So this time taking G as 10 meters per second square again, we want to find the total time of flight. To hit the ground. Okay. And then of course total distance and impact speed. So if it hits the ground at some time t, an impact speed like this. So I want to find out all this. Okay. Now just work out this question. Should be fairly easy. You can use either of the options of sign convention and this thing. Call it the Okay, so nobody got the answer yet?
Sir, it's a bad quadratic.
Okay, okay. So you use this thing, the discriminant method to solve it.
Sir, it's still bad.
It'll come in square root form, na, the time.
Yes, sir.
So leave the answer in root form. It's okay, no problem. Okay. So what I'll do is I'll go with the standard method, taking my y-axis here and my origin here. Okay. So I'll see that I'll write my displacement as 10t minus 5t square, because I'll take u as plus 10 and the acceleration as minus g. So now I'll see that at time t, which I want to find out, the displacement should be minus 160. So minus 160 is equal to 10t minus 5t square. So t square minus 2t minus 32 is equal to 0. So t is equal to 2 plus minus of 4 plus
128.
128 divided by 2. So that is 2 plus minus, I can take 2 common. So that's 1 plus 32. So square root 33 by 2. Okay. So the time that I'll get is 1 plus minus root 33 seconds. Now one of the roots is negative. Now this root 33 seconds you can solve like this. You can write this as 36 minus 3 to the power half. Okay. So you can write this as 6 into 1 minus 3 by 36 to the power half. Now you can use binomial approximation. We discussed once about binomial approximation, I'm sure, before. Right. So this becomes 6 minus 1 by 4. So that is. So you'll see that if I take 5.75 as an approximate value, it will be quite accurate. So time is either 1 plus 5 point, so 6.75 seconds, okay, or it is minus 4.75 seconds. So this will be an unacceptable route because we'll consider time to be only positive. Yeah. So, when you have some odd number like this, now, consider the closest one, which is a whole square. So one way is you can write it as 25 plus 8. Okay. Or you can write it as 36 minus 3. Even this will give you a reasonably accurate answer. So let's try this, for example. Here I can write this as 5 into 1 plus 8 by 25 to the power half. So that is approximately equal to 5 into 1 plus 4 by 25. This will give me 5.8. So two separate methods that I'm taking of using the binomial approximation give me slightly different answers, but rounded off to first place of decimal is okay. And if you use a calculator to find root 33, how much you'll get? Let's check out how accurate our calculation is around 5.75 only. It's pretty accurate, 5.75.
So there is
Okay.
another short trick
Now-
to find.
Yeah, tell me.
So if we have to find the square root of 33 and we have to find the small closest perfect square, that is a 6 and the root of that, and we have to divide 33 by 6 plus 6 divided by 2, we will get 5.75.
Okay, so what is the logic of that shortcut exactly?
So I did not know, but every time I check it comes out accurately.
Okay, okay. So just like find out about the logic of that method once, okay, before you use it. There are
Yes,
some
sir.
abstract methods in maths also. Okay. So just make sure that you know the logic of that method so that you don't make any mistake while applying it. But otherwise it's fine.
Yes, sir.
Okay, now the important thing is what is the significance of this negative root. So obviously we won't take this negative root. So the negative root is telling you that, see, when you write this equation that s is equal to this much, okay, it's telling you that from this point onwards, the displacement is so much, where at this point the velocity was 10 meters per second. And we started our stopwatch here. But this equation doesn't know that the motion actually started here. It could have been that the motion started from the ground below. You understanding? So it could have been a situation like this, that I projected this object with some initial velocity at some time which I recorded as minus 4.25 seconds. Then this object would have gone like this and come back. Now it would have reached here, okay, at a time of 0 seconds. From here to here, it would have taken that much time. And then again, it would have hit the ground at a time of 5.75 seconds or whatever. Okay. So that is the significance of this negative time. That suppose the motion had not started at this point, but actually started before this, it would still be following the same path from here to here. Okay. So if I started my stopwatch at this point of time, then this time when the motion actually started from the ground would have been 4.25 seconds before that. Okay, so that is the significance of the negative root. That's why the equation gives you a negative root. Though in this particular case, the negative root has no significance because actually the motion has not started before t equal to 0. Okay, people, so hope this point is also clear about the negative root. Okay. Now moving on. So now that we are done with vertical motion, we will look at 1D motion with variable acceleration. So the moment the acceleration is variable, we cannot use the standard equations anymore. Okay. What we have to use is calculus. So here the first case is if acceleration is a function of time. Okay. So basically acceleration is some kind of function of time. Then we will interpret acceleration as dv by dt, and we will integrate both sides. Okay. If some initial velocity is there, then v minus u is integration a dt from 0 to t. So it is integration of some kind of function of time, because the acceleration is some kind of function of time from 0 to t, or that is the area under the a versus t graph. That is the change in velocity. Okay. And once we do this, v will become u plus some kind of a function. Okay. So next we will interpret V as ds by dt, and we will calculate the displacement at time t by integrating this. Okay. So when we solve this, this will give us V also has some function of time, because the upper limit that we have taken is not a specific value of time. It is the instantaneous time t. So this equation will give us velocity also as a function of time. So then we can integrate that to get displacement as a function of time. Okay. So just note down this method, then we will discuss a couple of questions based on this. So this actually becomes a pure calculus thing now. It's no longer standard equations of kinematics. It's just a direct application of calculus and integration in particular. So the first type of situation is that if we are given the acceleration as a function of time and the initial velocity, these two things are known to us. Then from this we can find out V as a function of time. This will give us V as a function of time. And then from that we will get displacement again as a function of time.
So I didn't understand the second last step.
See, V minus U we got from that integration, no? Integration of A dt. So just
Yes.
take the U on the other side. So V becomes U plus that thing. Okay. Now that integration is giving us a function of time, no? Because the upper limit is variable.
Yes.
So, so from that my velocity is becoming a variable.
Yes.
Okay. So I can again integrate that with respect to time, but this time it will give me what? Displacement.
Yes, sir.
Okay. Got it now. Okay. Okay, so let's look at an example.
Just a second, sir. Sir, I'm stopping the.
Okay.
Yes, sir. Done.
Hmm. Okay, so now let's look at an example. So a body starts from rest at t equal to 0, moving along a straight line with time varying acceleration given by this. A is equal to 10 minus 2t, where acceleration is in meters per second square and t is time in seconds. So what we'll do is find instantaneous velocity and displacements as instantaneous quantities. Means as functions of time. Then find the time at which the body stops again, and find the distance traveled at an instant when the body's displacement equals to 0. Okay, so solving this question will cover all aspects, okay, and of things we have discussed. Okay. But you'll realize that this is out and out an application of calculus actually. Okay, we are going to be using integration all throughout. Okay, you can solve it by the definite integration kind of method I've shown above, or you can also use indefinite integration and remove the constant of integration, eliminate it by using the values that are given. So I'll show you both the methods, but generally I prefer using definite integration. It gives you a very precise method of solving. Okay, very good. Abhinav, Janvi, your answers are correct. Prithvi, Mansi. So let's check this out. So we start with this equation, okay, and this condition that it starts from rest. So u is equal to 0 at time t equal to 0, and the acceleration as a variable quantity is 10 minus 2t. So dv by dt is 10 minus 2t. So cross multiply the dt and integrate. And the preferable method is to use definite integration. You can also use indefinite integration and eliminate the constant. Okay. So this gives you the left hand side like this, okay, and the right hand side this. So the lower limits are 0 on both the sides, so it just becomes. So this is the first thing, velocity as a function of time. Okay. And once you got that, you interpret this as ds by dt. Now the definition of displacement is such that, okay, at t equal to 0, s is equal to 0. And at time t, the displacement is s. So this will give us s is equal to 5t square minus t cube by 3, correct, as a function of time. Once you got this, the rest is just about substituting values and all.
Sir, how will we find the distance?
Yeah, so that is the important thing here. To find the distance, you'll have to find when the velocity switches direction. Okay. So the velocity is initially what kind of quantity? It's positive. And then after 10 seconds, it will become negative. So velocity is becoming 0. So when you interpret this now, velocity, so you can see that velocity is equal to 0 at t equal to 10 seconds. Of course, u is also 0. So you can see velocity is positive from 0 to 10 seconds. And velocity becomes negative from 10 seconds onwards. So you don't need to plot the graph, but since it's a quadratic function, it's quite easy to plot the graph. So you'll see that the velocity has this kind of behavior. So in the positive direction, the velocity reaches a maximum at 5 seconds, but it switches direction after 10 seconds. So now see, if I calculate this area at some time with algebraic sign, then that will give me the displacement. Whereas if I just calculate the magnitude of the total area, that will give me the distance traveled. So this is clear now?
Yes.
Okay. Whereas if you also analyze the displacement versus time, you'll see that's an interesting equation in itself. So it's a cubic function which has a common root of 0 and another root of, how much is it? 15 seconds. So cubic function of this type would generally have a graph like this. Okay. But here 0 is the common root. So it will be like this. So we'll take only the positive side. Okay. So this is also showing you that the displacement becomes negative after 8 seconds. So it goes past the starting point after 15 seconds. graph would have been curving like this, but the negative side we won't take. Now this is telling us that this is 15 seconds. Now that should also tell you that if I calculate the area up to 15 seconds, I should get net area as 0 with algebraic sign for the velocity time graph. Okay, so this graph plotting is not compulsory here, okay. At least not in the question that I've given you. But of course, at JEE level, you can get a question where you have to select the graphs for the given. So suppose this is given, and one part of the question is that 4 graphs are given and select the correct graph for displacement versus time. So for example, you will also understand one thing, that the displacement will reach its maxima at the exact time when the rate of change of displacement is 0. So at this point of time, V will be 0. That's how I know that it's 10 seconds. So this is the maximum of the displacement on the positive side. Then of course, on the negative side, it goes to minus infinity if the time goes up to infinite. Now you see how all that analysis from calculus helps you out in these kind of situations.
So can't we just find an interval where both, the first initial velocity and final velocity both are 0, so displacement is actually 0?
No, beta, displacement is not 0 when initial and final velocity are 0. No. Displacement is 0 when it has returned back along the path on which it has gone. At that point of time, it will have a negative velocity. You're seeing here, the displacement is 0 at 15 seconds, but at the time of 15 seconds, it has a negative velocity, because it has to come back. You're understanding the point, no?
Yes, sir.
So what is happening is, from 0 to 5 seconds is going in the positive direction with increasing speed. Then from 5 to 10 seconds, it continues in the positive direction, but with decreasing speed, because you can see the slope is negative, but the velocity is positive. And then only from 10 seconds onwards, the direction of velocity is reversed. So actually from 0 to 10 seconds, it's going in the forward direction, but first with increasing speed, then with decreasing speed. You're following now, beta?
So just a second.
Just visualize the VT graph in terms of its slope. So slope is what? Acceleration, no? So just see what's happening in the VT graph and visualize the slope of tangent at different points. Then you'll understand.
So it's decreasing.
Yeah. So from 5 seconds onwards, the speed starts decreasing. And it comes to rest momentarily at 10 seconds. But when it comes to rest, is the displacement 0? No, because it's moved in the positive direction. You understanding, no? So it started from rest at t equal to 0. Okay. Then, for example, at t equal to 1 second, if you see, it has a positive velocity and it has a positive acceleration.
Yes, sir.
Then same thing is happening at t equal to 2 seconds. The velocity is positive, the acceleration is positive. But now at 5 seconds, momentarily the acceleration becomes 0. So this positive velocity is reached its maximum because the acceleration has become 0. Because after this, now what is happening is continuing in the same direction, okay, but with negative acceleration now, because the slope of the VT graph has become like this now. So that's why by the time it comes to 10 seconds, it's momentarily come to rest. So at t equal to 10 seconds, momentarily its V is 0, but it has a strong acceleration towards the reverse direction because even the acceleration is variable. So now it starts returning from here. So as it returns, now at 11 seconds or something like that, it has got velocity also in this direction. It has got acceleration. So it's again an accelerated motion, but in the negative direction. And this continues like this, and it finally returns to where it had started. We can see from the graph at 15 seconds. And after 15 seconds, it goes past this. So the displacement starts becoming negative. So this is how you can visualize the motion with respect to the two formulae that we have developed for VT and ST, or visualizing the formulae by the graphs.
Okay, sir.
So this is something you have to get used to a little bit, okay, but You will see that with the knowledge you have in calculus already, it's not going to be a problem at all. You just have to get used to applying it. We've done much tougher problems in calculus mathematically. Okay, so it's not going to be a problem technically. It's just that you have to get used to interpreting that information, right, in kinematics situation.
Yes, sir.
Sir, at t equal to 5 seconds, the body turns back, no?
No, beta. See, that's the point. जब body turn back करता है, what is its instantaneous velocity just at that moment?
0.
It has to be 0. Na? So now see in the graph when the instantaneous velocity is 0.
अच्छा हाँ 10 seconds, yes.
10 seconds. Na? 10 के just पहले it is positive and 10 के just बाद it's negative. So that is when it's switching direction. What is happening at 5 is that the slope of Vt is 0. Na? So that means the acceleration is 0.
Yes, sir.
Just before 5 the acceleration was positive. Just after 5 the acceleration is negative. So it's changing from acceleration state to deceleration state.
Yes.
Okay.
So it returns to its original position at 15 seconds, right?
Yes, yes. Okay, because returns to original means my displacement should be 0. So just
Yes.
look at the displacement time equation and put s equal to 0. So you'll get
Yes.
3 roots actually, 0, 0 and if you factorize it, it's t
Yes,
square
yes.
into something. So 2
Yes.
roots are common, 0, 0 and the third root is the 15 seconds, right?
Yes. So
Yeah.
so the deceleration is greater than the acceleration because while going it takes 10 seconds and while returning it takes only 5 seconds.
Yeah, that's something interesting that you can see over here. So you can say that, the average speed in the positive direction from 0 to 10 seconds is less than the average speed in the negative direction from 10 to 15 seconds.
Yes. Okay.
Because it takes, so that's correct. Yes. Okay, so let's answer the specific questions after this that find the time at which the body stops again. So that is, we found out that was 10 seconds, and find the distance traveled at an instant when the body's displacement is 0. So this is the part which we'll have to break up and calculate. So the third part is direct. V is equal to 0 at what time? So you can see that. Okay. And then fourth part, distance traveled when S is equal to 0. So from this you can see that displacement is 0 at t equal to 15 seconds. Okay. And the body turns back at t equal to 10 seconds. So the total distance we'll have to calculate like this. The distance traveled from 0 to 15 seconds will be the displacement from 0 to 10 plus the magnitude of the displacement from 10 to 15. Because 10 to 15, the displacement is a negative quantity. And actually that will just become double of this one because it's coming back the same distance. So what you need to do is you need to find out this value of displacement. S at 10. So S at 10 you can see is 100 into 5 minus 10 by 3. So 100 into 5 by 3. Or more precisely, 1000 by 3 meters. This is the total distance. So especially for JEE advanced level questions, this is one very important aspect of one-dimensional kinematics. When we have to make use of calculus, because the acceleration is variable, so we can't use the standard equations.
So can you scroll down a little?
Yeah. So that last part, the distance is 500 by 3 plus 500 by 3, because it goes 500 by 3 maximum displacement on the positive side and then returns back from 10 to 15 seconds by the same distance. So it becomes a total of 1000 by 3 or 333.3 meters. Right?
Yes.
Sir, if v is equal to 0 at 10 seconds, so the displacement should also be 0 at 10 seconds, no?
No, but a rate of change of displacement is 0, no? But see what has happened between 0 and 10 seconds. Velocity was positive all the way, no?
Yes, sir.
No, so what is the relationship of velocity and displacement? The displacement is the area under the velocity time graph. No? So just see the velocity time graph. From 0 to 10 seconds, you have the maximum positive area, no, actually. Because after that, the area starts becoming negative.
Yes.
You understanding the point of it?
Yes, sir.
Okay, so this question is fully clear now, all the parts, people. Any other doubt? Okay.
No, sir.
Most.
Now another, yeah, done now. Okay. Now another situation of variable acceleration, which we can come across. Okay. Now that's a little bit rare compared to this, because generally acceleration will, if it's variable, it will be given as a function of time. But another situation could be that we have variable acceleration given as a function of either displacement or position. So obviously, if the acceleration is varying with time, then it's also varying with displacement or position. because displacement of position themselves are varying with time. So if acceleration is a function of displacement or acceleration is a function of position, okay, then how do we proceed here? So we use chain rule, that acceleration which is dv by dt can be interpreted as dv by ds into ds by dt, and that is nothing but dv by ds into v. So the acceleration which is dv by dt can also always be also interpreted as v dv by ds. So once we use this, now given this that acceleration is a function of displacement, we can substitute this here. So we have v dv by ds, which is the acceleration, is a function of displacement. So we have v dv is equal to that function of displacement integrated with respect to ds. Okay. Now we use the standard this thing that at initial time the displacement is 0, and let's say the initial velocity is some u. So at some instantaneous time t, when the displacement is s, let's say the velocity is v. Okay. So the lower limit of the integration is that at t equal to 0, the initial velocity is u, and obviously the displacement is 0. And the upper limit is the instantaneous thing, that at some instantaneous time t, the instantaneous velocity is an unknown quantity, the instantaneous displacement is the unknown quantity. So this gives us v as a function of s. So from this we get, on the left hand side, we obviously get v square by 2 from u to v. And on the right hand side we get the area under the acceleration versus displacement graph from 0 to s. So v square minus u square by 2 is equal to this from 0 to s. So this is basically acceleration as a function of s integrated with respect to displacement, or in other words, it is the area under the acceleration versus displacement graph, not acceleration versus time, but acceleration versus displacement graph. So we will look at examples, but this is the second kind of application of variable acceleration that you should keep in mind. Okay. That if acceleration is variable such that it is given as a function of either displacement or position, then this is how we proceed. Okay. If it is given as a function of position, then same way, but we write this as dv by dx into dx by dt. So that becomes v dv by dx. So v dv by dx, being the acceleration, is a function of x position. So same way, now we integrate v dv on the left hand side from u to v, and whatever this function is on the right hand side from initial position x0 to final position x. There's only difference, the limit on the right hand side, because it's x position. So the initial position need not be 0, because I might have taken my origin somewhere else. So it is from the initial position, whatever it is, x0 to x. Whereas if I'm integrating with respect to displacement, obviously the initial displacement lower limit will always be 0. So just note down up to this. I scroll down and give you the final formula also.
Sir, can you please scroll down a bit?
Sir, can you go to the right side?
Which one? The
Position 1.
yeah. Okay. So it's just the difference in the limits of integration. Okay. Okay, so this is done now, na?
Yes, sir.
Okay. So let's see a quick example. So suppose we are given something like this, that a particle starts with u equal to, let's say, 2 meters per second at time t equal to 0 along a straight line such that its acceleration varies with displacement as a is equal to, let's say, 2 root s, where a is in meters per second square and s is in meters. S is the displacement in meters. Okay. So obviously the quantity 2 here has some unit. It has the unit of acceleration divided by square root of displacement. It's a physical constant. It's not just a numerical constant. Anyway, so what we want to do is we want to find its velocity v as a function of the displacement s. And secondly, we want to find its velocity v at an instant when its displacement is equal to 4 meters. When it's reached a displacement of 4 meters at that particular instant, what is the value of its velocity? We want to calculate this. Okay, so just try this out. Just use the method which I've shown above. Okay. It's a direct application of that. Okay, so I'm just checking out your answers, people. Yeah, seems to be correct.
Sir, mine is wrong.
Okay, let's check this out. Okay, so acceleration, which we'll write as b dv by ds, is equal to 2 root s. So this is one thing we'll use. Okay, and the other thing we'll use is that u is equal to 2 meters per second at t equal to 0. Okay, when s is 0. So we have to find out at t equal to t when s is equal to s. So cross multiply and integrate. So your displacement is going from 0 to s as your velocity is going from u equal to 2 to v. Okay. So it's a pretty simple integration. V square on this side from 2 to v. Okay. That side, the integration of root s is 2 by 3 s to the power 3 by 2. Okay. From 0 to s. Okay. So I think this is what we should be getting. V square by 2 minus 2 square by 2 is equal to 4 by 3 s to the power 3 by 2. Right. So we'll get v square is equal to 8 by 3 s to the power 3 by 2 plus 4, or v is equal to, now here we can see that everything is happening in the positive direction. So we will not take the negative root of after taking the square root. We'll take only the positive root, because we can see that the acceleration is always positive. The initial velocity was positive, the acceleration is positive. So the velocity can't be negative ever. It's not switching direction. Okay. So this is the answer to the first part. This is the velocity as a function of time. As a function of displacement. And second part, you have to just substitute this. So v at s equal to 4 meters. So just substitute s's value as 4. Okay, so you'll get again a square root number, but you'll get a value. So it's going to be pretty close to about 5 meters per second. Okay, so people hope this method is clear.
Yes, sir.
Okay, so this completes kinematics in one dimension for us, and this will be the portion of your upcoming major test. So I will send you a list of questions from HC Verma and the module to do, as well as a worksheet for some revision questions. So do all that, and like I think you will have some doubt session and all also this week later in the week. So you can resolve any doubts, or at any rate, you can always keep sending your doubts on WhatsApp when you're preparing for the test, especially, and I'll help you out with that. And then next week we will start projectile motion, which will be our first case of motion in 2 dimensions. Okay, Abhinav, no problem. If you haven't, anybody who hasn't got the HC Verma book now, I will send you the HC Verma exercise of kinematics. I'll just send you a picture of it. Okay, so you can work out the exercise questions. The book is only for doing the exercise at this stage, so don't worry. Okay.
Yes.
Sir,
Sir, I have a doubt.
Yeah, beta.
Sir, it's a question. Sir, in calculus.
Okay, can you send it to me on WhatsApp, beta? I'll send you a solution for
sir.
it. Okay.
Yes, sir.
I'll help you out with it.
Thank you, sir.
Yeah. Yeah, Sanvi, you had a question, beta?
the second last step.
Of
can
which
you
one, the
explain
first part or second part?
The left hand side part.
Left hand side part. Yeah. Yeah, second last step, how we got? Achha, see, transfer the 2 on this side. V square minus 2 square by
Sir,
2 is equal to
the above one, sorry.
which one?
Uh,
This step, limits.
when you've done, yes.
So see, on the left hand side now you have integration of v dv. So what is that? It's v square by 2. But what is the limit? The lower limit is u equal to 2. Upper limit is v equal to v. So it's upper limit minus lower limit, right?
Yes.
Similarly, on the right hand side, the integration is this, but what is the limit? 0 to s. So the upper limit is 4 by 3 s to the power 3 by 2. Lower limit is 0. So you're just substituting the limits now. So like, see, if I have this integration, x dx from, let's say, a to b, how I'll solve this? I'll first solve the indefinite integration. Okay. And then I'll put the limits now. So upper limit is b square by 2, lower limit is a square by 2. So I'll get this now. So that's the same thing, but instead of x, we have the variable v, and the lower limit is 2, the upper limit is v.
So where did that 2 come from? 2 into...
Oh, achha, sorry. That 2 comes in the next step. My mistake. Oh, no. That, achha, this 2 comes from this beta. This 2 root s, na? This 2 has come outside the integral. Na? And see, it's...
Acha, yes, sir, got it.
Got it, no? Yeah,
Yes,
that
sir.
2 is coming from. Okay, clear now, no? Okay, so that's it for today's session, people. Wish you all the best.
Thank you, sir. Bye, sir.
Okay,
Thank
have
you.
a nice day.
Bye, sir.
Bye, people.